In our previous lecture, we talked about how the total strains can be decomposed into elastic and plastic strains. And I should mention these conditions are under normal conditions at room temperature. If we have a situation where we have thermal strains or creep strains, we can do a similar type of decomposition and add those terms in here as well. But for our purposes, this is how we're going to approach this. So we have the total strains equal to the elastic and the plastic strains. The elastic strains can be expressed in terms of stresses through the use of Hooke's law. Sigma is equal to E epsilon, or we can rearrange that so that the elastic strain is sigma over E. And then we have the plastic strains, which we can use a formula that's related to the power law equation, and we can have the plastic strains equal to sigma over K to the 1 over N power. That's our Ramberg-Osgood description. Of course, there are other ways to describe plastic strains. There are other curve fits or equations, but this is the one that we're going to use in our class. We also had a little bit of discussion about what happens if we load a material and unload it. This just being a cartoon kind of sketch. If we have a metal initially up until the proportional limit stress, it's a really straight line. We start to yield it, and we have the curvy portion here. And again, the curvy portion can be described by the Ramberg-Osgood equation for the plastic strains. So at every point along this curve, like at this point, there's a combination of stress and strain. Okay. But that strain is a total strain, and that total strain is a combination of elastic and plastic strain. So if we were to unload this material, it actually follows an unloading path that is parallel to the initial portion of the stress-strain curve. So if that has the slope of the modulus of elasticity, so does that. And so what this means is at this point right here, we have a certain amount of recovered strain. That would be this portion of the curve. And we have a certain amount of strain that is permanent. That's the plastic strain right here. So this total strain location right here is composed of the elastic and plastic parts. Well, what we're going to do in this lecture is take a look in more detail at cyclic loading. So not only are we going to unload to zero stress, but we're going to actually reverse the load so that we have some compression, and then cycle it back and forth and talk about what things might happen and how we can model that kind of behavior. So let's first look at our waveform for cyclic loading. In the first case we'll look at is fully reversed. We've talked about fully reversed loading. We go up to a peak and we go down to a valley, and they're the same level of stress. So, we have like a plus sigma value here, and we have the negative of that down here. Now, previously we talked about rotating bending tests where we would have a sine wave that would connect these points. I'm going to draw these probably mostly in this section as just kind of a sawtooth type waveform. So up to the peak and down to the valley. For most metals, the exact shape of the waveform doesn't matter. For other materials, it may. It's just a little easier for me to draw it as a sawtooth in this section as opposed to those sine waves. And so this just kind of repeats on and on. I'm going to label a few points here. Maybe this is our first point, our origin point, and then point A, B, C, and D. And we can take a look and see what happens to the stress and strain response. And again, I do want to emphasize that the pictures I'm going to draw here are kind of cartoon sketches. Don't take them to be to scale. I will try to draw them as carefully as I can, but every once in a while it's just kind of hard to draw some of these, and they might be a little bit off. Alright, so here are my stress and strain axes. In undergraduate class, you typically focus on just this quadrant, this first quadrant right here, but we're going to look at the entire plot. So we start here at our origin point, and if we haven't tested our material before, we have zero stress and strain. And as we load it up, it's only going to be interesting for us if we load it past the yield stress of the material. So as we load it up, it has a linear elastic response, and then it has this curvy part as we talked about. And again, this is just a sketch, assuming that we have some plasticity going on. Okay, so that's what the shape of the curve would look like from O to A. Okay, so now we're sitting at A, and we're going to decrease the load to 0, and then we're going to put it into compression till we get to B. So we decrease the load to 0, and we're going to put it in compression. And that point here would be our point B. The value of the stress at that point, I'll bring it right here, would be minus sigma, and the value of the stress at this point would be our plus sigma value. Now we're down here at point B, and we increase the load. Now increase from a negative value. What we're doing is we're relieving the compression. Okay, so we have an initial elastic unloading segment again. So we have a slope of the modulus of elasticity, and it might even look like that all the way up to about here into the tensile side, and then it starts to curve over again, and we get pretty much to that same point, our point C. And if we were to keep going from C down to D, it would tend to follow this path and come down here. All of these slopes, the initial slope, this initial slope to unload, and this initial slope for unloading and compression, they all have the same slope, the modulus of elasticity E. This entire thing is called a hysteresis loop. And the length or the zone of the elastic unloading tends to be, it's, just as a rule of thumb, tends to be about 2 times the yield stress of the material in range. Some materials are different, but from here to here and here to here is a range of about 2 sigma yield. Okay. So if sigma yield, let me try a different color. If sigma yield on the uniaxial part of the curve, just the loading is about this point right here, we can make up a number, 100 megapascals. Well, then this range, before it starts to curve and yield and compression, would be from this tip about 200 megapascals. Likewise, this range here would be about 200 megapascals. Now, when we look at this curve, there are some things that look kind of interesting. Well, before we do that, we ought to define a term called the Bauschinger effect, and that is this idea that it yields about 2 sigma yield. So let's write that down. So if a material has been yielded, say for example in tension, then upon reverse loading, so specifically in to compression, it will yield again before minus sigma yield at a range from the extreme point of 2 sigma yield. Okay, so again, if this is sigma yield here, the negative of that value might be down here, but it's already started to yield because it went through a range of 2 sigma yield. So that's what the Bauschinger effect is all about, and you might hear that term throughout the semester. All right, well, let's look at this hysteresis branch in a little bit more, our hysteresis loop in a little bit more detail. We're going to talk about something called the massing hypothesis. U.S. people tend to call it the massing hypothesis. In Germany, they may call it Masing hypothesis. But in either way, what this is about is it's a description of these hysteresis loop branches. Okay, so what do I mean by a branch? The entire thing that I have here is a loop, but the loop consists of 2 branches. So this is a branch that goes from the tip down to the bottom, and this is a branch that goes from this tip down here up to the top on this picture. And we talked about how the Bauschinger effect said this range was about 2 sigma yield. This was about 2 sigma yield. And the initial loading, you know, we have the yield stress about here, and then it kind of curves like that. Well, there's an interesting thing that can happen, and maybe to highlight this monotonic behavior, let me go over this in red. So we have the monotonic stress strain curve. Looks like this. And we have the hysteresis branch that looks like this. From here to here is sigma yield, and from here to here is 2 sigma yield. And you know, from this point to this point, then we can kind of figure out what that would be, and we can figure out what it would be from here to here. And if we look at this the right way, those shapes are really very, very similar to one another. In fact, they're so similar that if we called this equation for the monotonic curve that epsilon was some function of stress, and for us, that's the Ramberg-Osgood description. It can be more general than just the Ramberg-Osgood description, but let's just say that epsilon is equal to a function g of sigma. Then this portion of the curve, see from O to A, looks very similar, similar in a mathematical sense and geometric sense, as this portion of the curve, the branch from O prime all the way up back up to here to A prime. And so what Bassing's hypothesis says then is if we have a functional description of the monotonic stress strain curve, then the functional description of the branch is going to look something like this. If we were to take and calculate the range of strain, okay, now we're talking about the distance along the x-axis from here to here, that range of strain can be computed as 2 times the function of the stress amplitude. Or the way you probably usually see me write it, if we take a look at the strain amplitude or the strain range over 2, it has the same functional relationship as the monotonic curve, where we put in the stress amplitude or the stress range divided by 2. So Bassing's hypothesis says that the hysteresis branch equation is functionally similar to the initial stress strain curve equation. But with stretched out axes. Alright, so again, if you can imagine picking this up and expanding it both in terms of up and down and left and right, then it would look just like that shape. I don't know, maybe I can try to do that on this picture. I haven't tried this before, but so I'm going to grab that, copy it, paste it. Let's clean it up a little bit. Take this and I stretch it out, and it's very similar to what I have here. Of course, you know, I didn't do it perfectly, but that's the basic idea of Massing's hypothesis. Alright, so let's take a look at what this means for our description of the stress strain curve, the Ramberg-Osgood equation. Alright, so epsilon is equal to sigma over E plus sigma over K to the 1 over N power. If we want to have an equation for a hysteresis branch, then what we do is we replace the strain terms with the strain amplitude. Remember, the amplitude is the range divided by 2. And then we replace the stress terms with the stress amplitude. And again, the stress amplitudes are the stress ranges divided by 2. Okay, so this would be our branch equation. But the thing we have to remember is that the branch equation doesn't start at the origin of the stress strain curve. The branch equation starts at the tip of the hysteresis loop. And the sign that's associated with it depends on whether we're having an increasing load or a decreasing load. Okay, so let's see if we can make that clear. So that would start at the origin. What I mean by that, on our stress strain axes, here's the origin. If I wanted to plot this, I would put this in Excel, and I would make a range of stresses, and I would calculate my strain based on the material properties E, K, and N. And it would go something like that. And now, if I want to unload, okay, my unloading origin would be at this point. And from this value, the change in strain from whatever strain value this is would be calculated based on this. And it would go, we do it in blue, it would change, and it would curve over till we get to here. And then at this point, we would use the branch equation again, using this as our origin. So we would take and we would calculate the delta strain points from here, and then we would end up at that spot. Okay, so this would be our branch equation. It might be useful if I try to illustrate this in Excel. More generally, what we can say to keep track of the unloading and the loading, if we want to use a sine function, SIGN, if we take a look at the sine of the change in stress and multiply that by the strain range over 2, then that would be equal to the delta sigma over 2 over E plus the delta sigma over 2 divided by K to the 1 over N power. All right, well, let me see if I can set up an Excel sheet that I think will illustrate this maybe a little bit better than just some of these equations that I've written down. Okay, so in order to illustrate what's going on here, let's first use the Ramberg-Osgood equation to plot the uniaxial stress-strain response. So I've made up some material properties. This might be typical of some kind of steel, though. So E here, there's our modulus of elasticity, 210,000 megapascals. K would also be in megapascals, let's say 1700. And N, I'm picking an exponent of about 0.2. These are kind of normal and reasonable values, and of course you can change these as well and kind of see how that affects the stress-strain response for the monotonic equation. So here I've decided to set the stress values at certain levels, every 50 megapascals up to 1,000. Now again, this is a fictitious material. It may break before 1,000 megapascals, but it's just here to illustrate our hysteresis branch equation and the Ramberg-Osgood equation. And based on that, then I calculated the strain, and we can see from this formula what I've done is here I've taken the stress value divided by the modulus of elasticity E, that's the elastic strain part of it, plus the stress value divided by K, all to the 1 over N power. And so as we go through, we can see increasing amounts of strain. And it might even be helpful if we broke this up into elastic and plastic components of strain. What we would find if we did that is that here we would have a little bit of plastic strain, but it might be very, very small numbers, like in the microstrain range. But as we start to get around here, we have increasing amounts of plastic strain. The Ramberg-Osgood equation is a continuously yielding equation. At every level of stress, the Ramberg-Osgood equation says you do have a little bit of plastic strain. This kind of goes counter to some of our models for metals, and that we don't have any plastic strain until we hit the yield stress. The differences are pretty negligible in the range of interest that we're going to be looking at for finite life materials fatigue behavior. But there are some interesting consequences to that we'll discover later on. All right, so with that, now I want to do the branch. So this is the monotonic equation. Maybe we can put a heading on that. But now we want to do the branch equation. So we're up here at 1,000, and we're going to go to minus 1,000. Okay, so I'm at 1,000, and let's do it every 50 again. And we want to go to minus 1,000. Let's see. Kind of took off on me. So there would be our range of stress values from plus 1,000 to minus 1000. So that looks like our sawtooth waveform from plus sigma to minus sigma. Okay, now we want to be a little bit careful here. We ended at 1000, so the stress range is going to be the place where we stopped minus this value. Okay, so let's do it this way. The absolute value of this point minus that point, and I could just put in 1000, but I kind of want to emphasize this. So when we're at the top, there's no stress range. Now let's see what we get as we go down through here. Down at the very bottom, we should be at 2000 for the stress range. Okay. So this is the stress range in reference to this tip point right here. All right, so now we want to calculate the corresponding strain range. Let's see what our formula says. So delta sigma over 2 divided by E plus delta sigma over 2 to the K to the 1 over N. So rather than have all this in one big giant equation, let's calculate the stress range divided by 2 in this column. That'll simply be this value over 2 . And if we go back to our equation here, what we're going to do is calculate the strain range from this equation. We'll talk about the sign in a moment, but the delta epsilon is going to be, take this 2 and multiply it by both terms, 2 times delta sigma over 2 divided by E plus 2 times delta sigma over 2 over K to the 1 over N. All right. So let's separate these out. Let's calculate this term. We'll calculate that term. We'll add them together, and then we'll multiply the whole thing by 2. Okay, I'm kind of spelling these out in kind of a very long format so we can see what we're talking about. I'm going to take the stress range over 2, that's this one. Now I'm going to divide it by the modulus of elasticity. Okay, now I'm going to take stress range over 2 and divide the whole thing by K. And I'm going to take that to the 1 over N. Stress range over 2 divided by K. And that whole thing to the 1 over N. actually row 4 here. Okay, so that looks better. So delta epsilon is going to be 2 times this quantity plus this quantity. Okay, so I have all those values. Let's scoot my graph over a little bit. All right, now the delta epsilon is referenced from this last point, so whatever, the 0.075, whatever. Okay, so the value that we would want to plot is going to be the last value on this part of the monotonic part. Take away the delta epsilon. Okay, so that's going to be the value to plot. Now, it's take away because of that sine function. When we're on the other part of the branch, and we'll do that in a minute, then we're going to be adding things. So that's where the sign comes in. I haven't put it in formally, but there's a minus sign right here. So what I'm going to do is I'm just going to take, if I've done everything right, I'll copy this and paste it into here. So this should be the strain part of the branch. The stress part of the branch should be the stress value decreasing. So fingers crossed, let's add this data set to it. The x values are going to be here, and the y values are going to be here. Okay. So this is what it looks like. This is the monotonic part. Okay, now this is the cyclic branch equation. Goes down to minus 1000. And we're going to do one more branch, and what it should look like is just the inverted part of this, where it comes up and reconnects at that spot. Okay, rather than having me, let me just kind of do this, pause the video and do this, and then we'll take a look and see what it looks like. Alright, so let's take a look. So for my increasing branch, I've kind of labeled it in the green. Basically, I just copied over these previous branch and pasted it over here. But my value increases from minus 100. I'm going to use a unit of 50 megapascals again, all the way up to plus 1000. From that, I can calculate the stress range from the tip. Okay, so it's minus 1000 plus L45. That is where I left off on the previous branch. I'll go over this all again in just a moment. Okay, so I calculate the stress range. When I'm down here, the range is 0. I only have an increase in range as I move up through here. And I do need the absolute value of that. We plug these numbers in as positive numbers into the branch equation. Calculate the stress range over 2. Calculate the elastic contribution. Calculate the plastic contribution. I calculate the change in strain, the delta epsilon. Okay, so what value of delta epsilon do I need? I calculate that. And then to make this plot, I don't want the delta epsilon plotted. What I want is each of these little points having an increasing amount, a more positive amount of strain. And so that's where this comes in. So I take the delta epsilon as reference to this final point, this Q45, which is where the previous branch ended. Okay, and so that's my hysteresis loop plot based on the massing hypothesis that we have to describe hysteresis branches. It might look a little prettier if I kind of drew it like that. Kind of had a little different aspect ratio. Alright, so let's review exactly what we did here in case some of this didn't make any sense. Maybe it'll make more sense now the second time we say it. What we've done is we've made an observation about metals under cyclic loading. That if we have fully reversed loading, we generate a hysteresis loop. On the stress-strain axes, we have an initial monotonic curve, and then we have the hysteresis loop branch. It's kind of hard to draw on this thing. Let me try that again. The whole thing is called hysteresis loop. There's a decreasing branch and an increasing branch, and the monotonic portion. If we have an equation for our monotonic curve, and our example is the RO, Ramberg-Osgood equation, we would say that the epsilon value is equal to sigma over E plus sigma over K to the 1 over N, with the origin here. Well, if we want to find a way to calculate the points along this hysteresis branch, we can calculate that by replacing the strain values with the strain amplitudes and the stress amplitudes by virtue of the massing hypothesis. Now, all these amplitudes just substituted in directly, but what we're usually interested in is the delta epsilon. So just like in my spreadsheet, I took this strain range over 2 divided by E, then I added it to the strain range over 2 divided by K to the 1 over N, and I multiplied the whole thing by 2. Now, the origin of the delta epsilons start from the highest point, the end of the monotonic curve. Or end of the last branch. Likewise, the delta sigmas start from the end of the monotonic curve or end of last branch. All right. So with this massing hypothesis, we can draw these hysteresis loops. Now the question is, how good is the massing hypothesis? Is it good for all materials all the time? The answer is no, nothing's good for everything all the time. But we're going to take a look at some real test data, and we'll be able to see how well the Massing's hypothesis does. All right, now in the next lecture, we're going to talk a little bit about something called the cyclic stress-strain curve, which can be a little bit confusing since we just talked about this monotonic stress-strain curve, but I think it'll make more sense in the context of cyclic loading, and then we'll also have some discussions of some of the transient effects that can happen under cyclic loading. All right, so let's stop here, and maybe we can, before we go, we can take a look at our curve again. Let me see if I can split this out. And just kind of play around with some of these numbers. Kind of auto-scaled on me. Let's see, let's change. Let's keep the maximum at maybe minus 0.1, the minimum, and then the maximum at 0.1. We can look at values that are smaller than the k that I picked, greater than the k that I picked. Can change the n value, and we can play around with this and see what values affect, how these values affect the response that we're modeling here. All right, so we'll pick up talking about more cyclic behavior in the next lecture.